For this tutorial, I want to cover how important pointers are when it comes to dynamic memory allocation. In the C language, one major advantage of a pointer is that it allows you to have direct control of how you can access memory. And this is really powerful when it comes to building complex data structures or when trying to save space when allocating memory. For example, if you want to dynamically set the size of an array based on an external input that's not known beforehand to the compiler, or if you want to change the size of an array at runtime, this is where the power of pointers is demonstrated. And what I mean by that is arrays have a constant size that cannot be changed. But with pointers, you can allocate the amount of space or memory that you need. And in turn, this allows you to improve your program's space efficiency. And it allows you to shape the data that's based on the user's needs. Before we dive into why pointers are so awesome when it comes to dynamic memory allocation, let us first get a general understanding of how memory allocation works. Memory allocation is the process by which a program is assigned physical or virtual memory space. And this allocation is done either before or at the time of program execution. And there are two types of memory allocation. They are static and dynamic. With static memory allocation, memory is allocated in a stack for declared variables by the compiler during compile time. Whereas with dynamic memory allocation, the memory is allocated in a heap at the time of execution or at runtime. Malloc and Calloc are functions that are used and are assigned to pointer variables. To demonstrate stack memory, let's take a look at these two codes, function 1 and function 2. They call one another, so it's an indirect recursion. And on the right hand side, this white canvas, this is our stack memory frame. And the way it works is that whenever a function is called, an activation record is created. So for example, when main is called, an activation record is created. And inside main, function 1 is called. And I'm just going to abbreviate function 1 to F1. An activation record is created. And inside function 1, we have our int data, and we have the print function, and then function 2 is called. So an activation record is created for F2. And when we go inside of F2, again, we have an integer data, we have a print statement, and then function 1 is called. I'm not going to go through the whole thing because the whole point here is to show you how activation records are created on a stack frame. And as you can see, the stack memory is very organized. And with the stack frame, after the execution of the function is automatically destroyed. And then after we execute function 1 is automatically destroyed. As you just saw, the stack was used to store the order of the method of execution. So all in all, with static memory, variables get allocated permanently until the program executes or the function call finishes. Allocation is done before the program execution, and static memory uses the LIFO order, the last in, first out, as far as when the activation record is popped from the stack. The static memory is also less efficient. No memory reuse is allowed, and once memory is allocated, the memory size cannot change. Also, we cannot reuse unused memory in the allocation scheme. One advantage of static memory is execution is faster than dynamic memory allocation. And finally, memory is allocated at compile time. Now let's talk about dynamic memory. In dynamic memory allocation, variables are only allocated if the program gets activated. This allocation is done during the program execution. It uses the heap to manage the memory allocation, and it is more efficient than static memory. There's also memory reusability, and the memory can be freed when it is not required. Once the memory is allocated, the memory size can change. So there's more flexibility when it comes to managing memory. A user can allocate more memory when required, and a user can release memory when the user needs it. The execution, however, is slower than static memory allocation, and memory is allocated at runtime. And finally, the allocated memory can be released at any time during the program. Now let's talk about the heap. Think of the heap as the portion of memory where the dynamic allocated memory resides. Let me illustrate this using this white canvas on the right. So the top portion, I labeled it the heap memory, and the bottom portion, I labeled it the stack memory. Prior to this point, if you've never used pointers, all you've been working with has been coming from a pool of memory known as the stack. Now, the way that you would use the heap is very similar to how you would use a resource. A resource is something that you can request to use, and once you are finished, you can free it, but you're not required to free it. Similarly, the heap memory is something that you can request, you can use it, but you're not required to release it. In other words, memory is not automatically destroyed in the heap. Unlike the stack, however, a program cannot directly access the heap. The only way to access the heap is through pointers. Let me illustrate this on the right-hand side. The top part is the heap portion of the memory, and the bottom part is the stack portion of the memory. And this pool of memory is basically shared by both the stack and the heap. So you can start filling up from the bottom with the stack. Vice versa, you can start filling down from the top with the heap. In other words, you can run out of stack memory by going all the way up, and this is known as stack overflow. And you can run out of heap memory by going all the way down. You can obtain memory in the heap by using two functions, Malloc or Calloc. Let's start with Malloc. Malloc stands for Memory Allocator. It allocates a single large block of memory with the specified size. The Malloc function returns a void pointer to the allocated memory of the byte size, so therefore the return pointer must be typecasted to the pointer type, or the return pointer can be typecasted to any pointer type. Now, once we allocate memory in the heap through Malloc, the only way we can access that memory is through pointers. Before I code an example, let me go over the general format. So here we declare a pointer, and then once we malloc memory into the heap, we assign that block of memory into pointer. Now let's go over to the left-hand portion of our screen so I can code an example. Using malloc, let's go ahead and create an array inside of our heap. And so let's first declare a pointer. We'll just call it PTR. And then what we want to do is we want to allocate memory in our heap by using malloc. We need the size of bytes. Let's just say we want a size 4-element array, and then we're going to use the size of operator, and then we're going to do size of int, which is 4 bytes. And let's go ahead and assign value into our array. So we're going to use a for loop. This should give it the values of 0 to 3. And let's go ahead and create a print statement. And let me run this. Okay, that works. And let me just make the values a little bit more distinct by multiplying this by 2. So that way our values does not equal our indexes. So let me illustrate what's happening here. On line 10, a activation record is created for main. And inside of main, we declare a pointer, PTR. And on line 13, we use the malloc function. And we use the size of int, and we create 4 memory blocks. Each of these memory blocks are 4 bytes. The only way we can access this is by using a pointer. And so on line 13, we assign this address into this pointer. So this points to the first block. And then on line 15, we jump into the for loop so we can insert values into our dynamically allocated array, and it starts out at 0. So at index 0, we multiply it by 2, and 0 times 2 is 0. And then we increment I with I++, and we get to 1. And so 1 times 2 is 2. I is incremented to 2, and we jump to line 17. 2 times 2, this becomes 4. We go back to the loop again. I is incremented to 3. Line 17, 3 times 2 is 6. And if I compile it once again, 0246, 0246. We can also use pointer arithmetic to print out elements of our dynamically allocated array. So let me delete this. So let's say we want to print out the last element using pointer arithmetic. We would just simply type PTR plus 3, but make sure that you put that inside of a parentheses and put an asterisk in front of it. We'll print this first, so this should give us 6. There it is. This is what happens when you don't put the parentheses. It's going to give you 3. And why is that? Because of order of precedence. So PTR right now is pointing at 0. And so it's dereferencing our first element. And so this is 0. And if you add 3 to it, it's going to give us the value of 3. Here, if I do plus 5, it's going to give us 5. And so that's the reason why you want to put the parentheses. If you wanted to print out the value 2, you would just simply say PTR plus 1, because this is address 0x200, and then you add 1 to it, you're really adding an increment of 4 bytes. So this should print out this address, and we should get the value of 2. There it is. Let's go back to line 13. There is one other thing that I forgot to do. If you look at the syntax here on the right hand side where it says type, we want to typecast it for best practice. So here I'm just going to type in int star, and if I run it, I should get the value of 2. The last thing I want to do is I want to uninitialize the values for this dynamic array that we created. So I'm going to comment this out, and I'm going to printf, and let me also comment this out. And when I print it, notice how you're getting junk values. And finally, the last thing that we want to do is we want to free this memory that we created right here. So unlike the stack, there is no garbage collection for the heap. Stacks are popped off, whereas the heap, it stays there unless we free it. And if we don't free it, obviously it can create a memory overflow. And so the way you free it is you would just type free and then PTR on the inside. Let me comment this. There it is. It'll print out the second element. And if we copy and paste this here, and I'll just put after free, notice how it's freed up. It's given us some junk value. Now let's go over Calloc. Calloc stands for Contiguous Allocation. And what that means is it allocates multiple blocks of requested memory, whereas Malloc only allocates a single block of requested memory. As far as format, Calloc returns a void pointer, and unlike Malloc, which only takes in one parameter, Calloc takes in 2 parameters. The first parameter is the number of elements, and the second parameter is the size of bytes requested. Here's an example of the syntax. Let me show you another difference between Malloc and Calloc. So let me take this out, and let me comment this out, and let me print this again. And so with Malloc, when you print it and it's uninitialized, you get junk values. Let me do the same thing with Calloc. So let's change this to C. First parameter is the number of elements, so we'll say 4, and then the size of int. So now when I print it uninitialized, this is what you get. You get all zeros. So that's one major difference, is that Calloc automatically initializes each element to 0 if you don't initialize it yourself. And obviously if you initialize it, you'll get the initialized values. But let me only initialize the first 3 elements, and notice how the last element will be initialized to 0. So that's the major difference between Calloc and Malloc. Calloc automatically initializes it to 0, and also Calloc is a little bit more expensive when compared to Malloc because it does initialize every element to 0. So for example, let's say you have 1,000,000 elements. Calloc is going to take longer to print or compile because it's initializing uninitialized elements to 0, whereas Malloc, it won't do that. So it does come at a performance cost. And finally, don't forget to typecast it for best practice, and do not forget to free the memory. And one last thing I forget, and this is for both Malloc and Calloc, is after you free it, set it to null. So PTR equals null. So the pointer will become a null pointer. And after I free it on line 28 and set it to null on line 29, if I print it, notice how the memory is freed. It doesn't give us a return 0. In short, do not forget to typecast it, do not forget to free it, and after you free it, do not forget to set your pointer to null. Now let's talk about the realloc function. Realloc is a function that we can use to increase the space that we've already allocated in the heap. For example, if the memory that we allocated by Malloc or Calloc is not enough, Realloc can increase that memory. In terms of format, Realloc does return a void pointer, and it takes in 2 parameters. The first parameter is the pointer that we are trying to increase, and the second parameter is the size that we want to increase. And here's an example of how we would use Realloc. So let's go over an example on the left-hand side of the code, and I'm going to go ahead and delete this. And let's say we created a dynamic array of 4 elements. And let me go ahead and print. So here we have 0, 2, 4, 6. Now let's just say I want to increase the size of that 4 elements to 8 elements. And I want to store 4 more elements into this dynamically allocated array. This is where we use Realloc. So the way that it works is I would simply assign the reallocated memory to PTR. And then it takes 2 parameters. The first parameter is the memory block that we want to change. And in this case, PTR, because this is what we're trying to increase. And then the second is the amount that we want to increase it to. And in this case, we want to increase it to 8. So 8 times the size of int. Now keep in mind that PTR will still contain the original values of 0, 2, 4, and 6. And if I print it, let me copy and paste this, and we'll just say after realloc, it still has 2, 4, 6, and 8. This is probably better. Okay? To add on the new data for our newly created elements or memory, we would just use a for loop. So I went ahead and created a for loop. It basically mirrors our first for loop where we're just multiplying the index by 2. But the difference is on the first for loop, I started at 0 and I went all the way up to index 4. But in this for loop, since I'm adding at the end, I'm starting at index 4. And the reason why I'm starting at index 4 is I ended at index 4, but we're actually going to index 3 because it's less than 4. So here we have to continue where we left off because 4 is not inclusive. And so we start at 4 and we're stopping at index 7 and we're multiplying each index by 2. And that's how we get 8, 10, 12, and 14. When we print it, I'm using the same print statement. It should give me all of the new elements, including the old ones. So let's run it. Here's the old element 0, 2, 4, 6, which came from this print statement from line 20 to 23. And after the reallocation, where we reallocated more memory at the end, we added 8, 10, 12, and 14. So the size of our array increased. So how does realloc work and what is going on under the hood? So when realloc, if you look at line 25, takes in the original pointer as a parameter and it's returning a new pointer, realloc does not always return the same pointer. And what I mean by that is that the data typically stored in a contiguous manner. To illustrate this point, I went ahead and created a print statement that prints the address of our pointer before the realloc and after the realloc. Once I run this, notice how the address before the realloc is identical to the address. Now this is the beginning address of our dynamically allocated array. And notice how it's identical, 008A to FA0. So let me draw that on the right hand side to illustrate it. So what's happening is we have our allocated dynamic memory in the heap with 4 elements. And we have 0, 2, 4, and 8. So what realloc tries to do is when we increase the size of this memory by 4 more elements, Realloc will try to allocate the new memory next to this current pointer. So it'll try to allocate it here. And let me use a different color. If this is 0x200, this is 0x204, and it's incremented by 4 bytes all the way across. So in this case, we'll have 10, and once we get up to line 30 to 33 and fill in the data, we'll have 10, 12, 14, and 16. Actually, my numbering is off. It should be 2, 4, 6, then 8. So let me fix this. As you can see, the memory is contiguous. Now, in the situation where this is not available in the heap memory, what Realloc will do is it will find a new space in the heap memory. Let's say somewhere here, away from this memory, and copy the existing data to the new memory space. So in this case, it will copy 0, 2, 4, 6. It will then add the new data starting on line 30 here, 8, 10, 12, and 14. So this is the new data that we get starting on line 30 and the new allocation. And this will be a completely different address. So let's just say this will be 0x300. I want to demonstrate the situation by creating another pointer. So here on line 28, I've created another pointer called PTR2. And on PTR2, I'm assigning memory in the heap, size 4 array, and I'm just going to assign 4 to it. And then I'm going to print it, and I'm going to print its address. But before I do that, let me comment out this whole block. And let's just, again, take a look at the address of PTR before the Realloc and the address of PTR after the Realloc. And notice how it's completely identical. So in this case, we are getting this condition where it's just adding on to the end of our particular memory space that we've already allocated. So it found some space, so it's just adding on to it. Now let's take a look at this condition where this space isn't available, and I'll have to create another space in memory and copy down the first 4 element and then add on the last 4 element. And that's where PTR2 comes in. So let me uncomment this, and now let me print it. And notice how the address of PTR is now completely different. PTR's address versus the after the relocation. And notice how PTR2 it's making this space unavailable. So what it's doing is it's copying the first 4 elements and creating memory and creating space in another area. Instead of %P, let me change it to %D so we can get an idea of how far the memory, and let me run that. And so this is at 64, and notice how PTR2 is taking the memory space right after this, and then it copies it onto a completely different memory location. Now before you use Realloc, there are some food for thought to consider. What happens to the data in the old space, and in this case, this space right here, the 0, 2, 4, 6. If we're copying that onto the new space, and being that the heap is not the stack, so there's no garbage collection, and we haven't freed that space, let me go to line 44 and create a new pointer. And it's going to be an int data type, and I'm going to call it old space. And what I want to do is I want to assign the address of PTR to it. And here on line 63, I'm going to print out the address of old space so that we can compare it to the address of PTR. It should be the same as the first PTR. And then I'm going to print out the data of whatever old space is holding. And let's go ahead and print that out. Okay, so this is the PTR, and the address of it is 122018888. And then this is PTR2, and then this is the reallocation when we added 8, 10, 12, and this is the address of PTR after the reallocation. Notice how it's different. But here we set PTR is an address variable, into old space, and notice how the address is the same. And now when we printed out the data of whatever was left in old space, the first 2 spaces it gave us garbage values, but look at the last 2, it still kept some of the old data that was left in there. And so what happens if this is a piece of password or some sensitive data that you have in there? It poses a security question. So you really have to be careful of what may or may not be left in the old space once you reallocate into the new space. And one last thing about Realloc is that we cannot use it after we free the heap. So we can't use it after line 71. And finally, make sure that if you intend to use the Malloc, Calloc, and Realloc functions to include the stdlib.h library. So in summary, when working with dynamic memory allocation, memory is allocated at runtime from the heap segment. And the three functions that can access the heap are Malloc, Calloc, and Realloc. And these functions return a pointer to the memory. So in short, the only way you can access heap memory is through pointers. Malloc stands for memory allocation, and this function reserves a single block of memory with a specified amount of bytes. The Calloc function is short for Contiguous Allocation, and this function reserves blocks of memory with a specified amount of bytes. And Realloc, which is for reallocation of memory, is used if the previous allocated memory is not sufficient enough that more memory space is needed. And finally, the free function is used to deallocate memory or to free the used memory that is occupied by Malloc, Calloc, and Realloc. Since the heap does not have garbage collection, it is up to the user to free up the memory. Otherwise, it can affect system performance and take up memory space. It is also a good practice to set the pointer to null after freeing the memory. All in all, dynamic memory allocation allows the user to change the size of the data structure during runtime. Thank you for watching.